A couple other announcements. We're going to skip section 18.13 on nucleophilic aromatic substitution. It's okay if you've already read it because it sometimes does show up on our standardized final exam, but we don't have time to fit it in this part of the class. It won't show up on exam number 1. We're just going to focus on the electrophilic aromatic substitutions. Exam 1 is starting next Wednesday through Friday. So we're going to have our Zoom question and answer session from 7 to 8 on Tuesday. And the review, the outline of topics that we film and post on Learning Suite, we'll do that today. So probably by about 5 o'clock today, that will be available. The link to that will be on Learning Suite for you to take a look at. So please start preparing for exam 1 now. We also have a sample exam 1 on Learning Suite, so you should work that, especially if you're new to the class and weren't in 351M with us last semester and are not familiar with the format of the exams, the types of questions, the length of the exam, then the sample exam will help you with all of that. So today we're not quite going to finish chapter 18. We'll finish it at the very beginning of class on Monday before we get into 19. We'll talk about 3 topics today: limitations of electrophilic aromatic substitution reactions, performing the reactions on di-substituted benzenes. If we have 2 substituents on a benzene, where does the 3rd substituent go? And then we'll conclude by talking about some reactions that occur on the substituents themselves, transforming one type of substituent into another. So here's our hierarchy of activating and directing effects that we talked about on Wednesday, and we'll refer to this as part of our discussion today. As we start out with some of the limitations of our electrophilic aromatic substitutions, we'll focus on first on the halogenation reactions of strongly activated benzenes. Okay, so a strongly activated benzene would be one that has either an ether, an alcohol, or an amine attached. Those are our strong activating groups. We'll talk in a moment about why this one is kind of medium, not quite as activating as these 3. And then, of course, the alkyl groups, because they only donate by induction and not resonance. We know that alkyl groups are weaker activators. But if we have a strongly activated benzene, such as aniline, okay, remember we have our 3 common names that we need to know, and aniline is one of them. If we want to perform halogenation under our standard halogenation conditions, we are going to get a polyhalogenated product. Okay. Our strong activating groups are orthopara-directors, and we're going to halogenate at all the positions. Okay. So it turns out that the halogenation reaction is the easiest or the most facile of our electrophilic aromatic substitutions. It has the lowest activation energy for that rate determining step, meaning that the electrophile in this reaction is the most electrophilic of the electrophiles in our 5 different electrophilic aromatic substitutions. And so you'll recognize that the bromine is a weak deactivating group. So we attach 1 bromine to the ring, and that's going to reduce the reactivity of the product, but not enough to prevent us from attaching a 2nd bromine and then a 3rd bromine. Okay? So if we limited the amount of bromine, if we had excess bromine, of course, this is the product we would get. We'd get exclusively this product. If we limited the amount of bromine, we would end up with mixtures of products. We would have some monobrominated, some dibrominated, some tribrominated, and then some unreacted starting material. So we'd end up with a mess. And we don't want messes. Usually when we're doing organic reactions, we want clean processes that give us a single product, or at worst, 2 products that we can separate. So how do we solve this problem? There's actually 2 ways we can solve it. One is, if it's an amine, an NH2 group, we can reduce its activating properties by acylating it and forming an amide. Okay? So this is a medium strength activating group as opposed to a strong activating group. Why would this amide not be as activating as the corresponding amine? Any ideas? Okay, Grace? Okay, it's more sterically hindered. That's true. There's another reason as well. Go ahead. Yes. Mm-hmm. Yes, so this nitrogen is part of an amide. We'll discuss amides in our next section of the class, but we already know that a carbonyl group is electron withdrawing. We learned that in chapter 16. And so we can have a resonance structure where this lone pair turns into a carbon-nitrogen double bond, and then we have a negative charge on the oxygen. So that shows us that we can delocalize that lone pair on nitrogen into that carbonyl group as well as into the benzene ring. Okay? So because there's two ways we can delocalize that lone pair, it is not donated as strongly to the benzene ring as it is in aniline. If we had just the amine, now there's only one place to delocalize that lone pair, and that's into the benzene ring. So this is not as strong of an activator as this. And so in this case, if we perform the bromination, now we will get just the monobrominated product because we've now reduced the reactivity enough by attaching this weak deactivating group that this would react significantly slower than that, and we'd be able to consume one equivalent of bromine and get just monobrominated material. Of course, we would have two monobrominated products because the amide is an orthoparadirector. So we would have something close to a one-to-one mixture of these products, which we could separate, but we would only get monobrominated material. Okay? So that's one solution to this polyhalogenation problem. There's another solution, and that is simply leave out your Lewis acid. We learned back in Chem 351M that halogens are electrophilic because they're polarizable. If you bring a nucleophile, such as an alkene, close to a halogen, they'll react. Okay? We reacted alkenes directly with halogens in 351M. We didn't need any Lewis acids to activate those halogens. Now, with a normal benzene ring or a moderately activated benzene ring, we do need the Lewis acid. But if we have a strongly activated benzene ring, one with either an ether, an alcohol, or an amine attached, we can react that directly with a halogen, chlorine or bromine. And that halogen is electrophilic enough that the strongly activated benzene will attack it directly without the aid of a Lewis acid. But then, once we attach our halogen, now this ring is not strongly activated, right? We have a strong activator and a weak deactivator. We've attenuated the reactivity enough that we're now able to stop at the monohalogenated products. So two ways to solve this problem. The problem is derived from the fact that halogenations have the lowest activation energy, the most electrophilic electrophiles. The way to solve that problem of polyhalogenation is either making an amide, and that works if your group is an amine, or leaving out the Lewis acid. That works if it's an amine, an ether, or an alcohol. Okay? So multiple ways to get monohalogenation to solve this polyhalogenation problem. Any questions? Yes, please. So when we have a medium, kind of a medium activating group, and then we attach a weak deactivating group, now the reactivity is too low for the polyhalogenation to occur. If we had a strong activating group and a weak deactivating group, then we'd be able to have the polyhalogenation, which we see here with the amine. But it's just somebody empirically determined this in the lab. They found that if they converted this amine to an amide, that they could stop the reaction at monohalogenation. And that's just due to the fact that this is not as strong an activating group as that. Okay, other questions? Yes? Alcohol, ether, and amine. So these three at the top of our chart are the ones that are going to cause polyhalogenation under the normal conditions, right? Because in all three of these cases, those lone pairs are only delocalized into the benzene ring, unlike this group where the lone pair can be delocalized into two places. All right, so our next limitation is going to come from the fact that our Friedel-Crafts reactions, both the alkylation and the acylation, are the most difficult or the slowest of our electrophilic aromatic substitutions. So the electrophiles, in the case of the Friedel-Crafts reactions, are less reactive than the electrophiles in our other electrophilic aromatic substitutions. So we'll have higher activation energies, slower reactions. And so there's a consequence to this, which is that Friedel-Crafts reactions will not occur if we have a meta-director attached to the ring. Okay. So any of the groups below this dashed line, they all end up putting a partial positive charge or a positive charge on the atom attached to the benzene ring. They deactivate the ring sufficiently that Friedel-Crafts reactions will not occur. They will occur with weakly deactivated benzenes. If we just have a halogen on there, the halogens are weaker deactivators than these groups, and we talked about why that was on Wednesday. So Friedel-Crafts reactions will occur with halogens, deactivating ortho-para-directors, but not with our more strongly deactivating meta-directors. Okay? Interestingly enough, the Friedel-Crafts reactions will not occur with strongly activated, with anilines. Okay? If we have amines, which are our strongest activating groups, we cannot have a Friedel-Crafts reaction. This doesn't seem to make much sense, but let's think about it. What would be the problem with trying to perform a Friedel-Crafts reaction with aniline? Any ideas? So let's look at this functional group. What would we classify this as? Acidic, basic, nucleophilic, electrophilic? It's basic. It's both, it's a weak Bronsted base. It's also a Lewis base. Remember, in our Friedel-Crafts reactions, we have to add Lewis acids. And we want those Lewis acids to coordinate to our alkyl chloride or our acyl chloride. But if we have a strongly Lewis basic group, such as an amine, that Lewis base is going to react with our Lewis acid instead of the Lewis acid reacting with the alkyl or acid chloride, and will generate a Lewis acid Lewis base complex. Okay? And you see in our Lewis acid Lewis base complex, we have a formal positive charge on the nitrogen attached to the benzene ring. So we've now turned a strong activating group into a strong deactivating group. Now this formal charge is not +1, right? These are just formal charges. They're probably closer to 0 than they are to 1, but it's big enough to make this group in this deactivating meta-directing range and therefore unable to undergo a Friedel-Crafts reaction. Okay? Now, nitrogen is more basic. It's less electronegative, so it's more basic than oxygen. We don't have the same problem with our oxygen groups because they're not as Lewis basic. They will allow the Lewis acid to react with the alkyl halide or the acid chloride. It's only the amines that have this problem. Okay, so no Friedel-Crafts reactions on metadirectors or with amines attached to the benzene ring. Okay. We have another problem with Friedel-Crafts. This is a problem just with the alkylation. Okay. And this problem comes from the fact that the Friedel-Crafts alkylation is the only one of our 5 electrophilic aromatic substitutions that adds an activating group to the benzene ring. Okay. We add an alkyl group, which is a weak activator, but it is an activating group. So we're making a product that is going to be more reactive than our starting material. So that product is going to react faster with our alkyl halide and our aluminum trichloride. And then we're going to get polyalkylation. We'll just draw the products from dialkylation here. Okay. So you're going to get mixtures. If you use close to a 1-to-1 ratio of these components, you're going to get mixtures of products because of this polyalkylation. Okay. So the way to solve this polyalkylation is to use a large excess of your benzene. Let's say you have a 10-to-1 ratio of benzene to your alkyl chloride. As you start to produce your monoalkylated product, yes, it will be more reactive, but it will also always be in a much lower concentration than your benzene. So if you make sure your benzene is always in a much higher concentration than your product by using excess, then you can obtain just the monoalkylated product. Of course, that then requires you to separate the benzene from the monoalkylated product at the end of the reaction. Usually the monoalkylated product will have a higher boiling point, so you would be able to use distillation to do that separation. Okay? Any questions about why we get polyalkylation and how we solve it? Okay. In contrast, we don't have polyalkylation with, or polyacylation, I should say. If we're performing a Friedel-Crafts acylation, we end up making a ketone. We know that that ketone is polarized. We end up with a partial positive charge on the carbonyl carbon attached to the benzene ring. So we have attached a deactivating group to the benzene ring. So this wouldn't react at all, in fact, in a Friedel-Crafts acylation, because this is a strong deactivating group. Okay? So no problems with polyacylation, only with polyalkylation. Any questions? All right, let's talk about how we would synthesize di-substituted benzene derivatives from benzene itself. If we have 2 substituents attached to the benzene ring, then we would have, in theory, 2 different ways, 2 different orders that we could attach those substituents. Sometimes we might be able to make both, but other times we might only have one way that we could do this. Okay, so let's take a look. Let's say we're going to make paranitrotoluene. What are the directing effects of that methyl group? To which carbons will that methyl group direct substitution? Okay, it's an ortho-para director. In this case, the para position is blocked. We already have a substituent there. Right, so that methyl group is only going to direct to the ortho position. Okay, what about the nitro group? Okay, that's a meta director. And the carbon meta to the nitro group is the same as the carbon ortho to the methyl group. So we're in business in this case, in that we would be able, oh, never mind. This is not the topic I mentioned of which order we would be able to put these groups on. This is the topic of to which carbon a third substituent would go. So I'm sorry I got ahead of myself in the discussion that we were having. So let me put, we're gonna erase these arrows. We're gonna come back to that. Sorry about that. So we've already established that this is an ortho-para director and this is a meta director. So if we're doing a retrosynthesis, which of these groups do we want to remove from the ring in the retrosynthetic direction? Yes. The nitro group, yes. If these groups are para to each other, we can't make them para to each other if we have the meta director on first. Okay, so we have to put the meta director on last. Okay, so we'd have to use toluene, and then of course we can go from toluene to we could go backwards from toluene to benzene. That would be very easy. And then in our synthetic direction, we would do a Friedel-Crafts reaction. Of course, we'd have to use excess of our benzene to make sure that we got a mono alkylated material. And then we could perform a nitration. Okay. In this case, we would get two products. We can't avoid getting two products in some of these reactions. And so we would just separate. We would acknowledge that we are forming two products, but then we would just separate them. Okay? Let's do another one, and then we'll go back to that other topic that I tried to jump ahead to. Okay. Nitro group, we already know that's a meta director. What about our ketone? It's also a meta director. Okay, so we have two meta directors meta to each other. We should be able to use either order to install those groups. Will that work in this case? Or is there going to be a problem with one of the possible ways of making this product? Yes? Okay. So you're both strong deactivators. What reaction do we need to use to install our ketone? We need to use a Friedel-Crafts acylation. Remember, Friedel-Crafts acylations do not work with meta directors already on the ring. Okay? So we could not install this group if we already had the nitro group. Okay? So we're going to have to perform the Friedel-Crafts reaction first. Okay. Now this reaction is going to be slow because we have a strongly deactivated benzene, but it will work. Right? Nitrations, sulfonations, and halogenations, all those will work with meta directors. It's only the Friedel-Crafts reactions that don't. And so here we end up with the desired product. Okay? So we have to consider activating or deactivating and directing effects when we are planning a synthesis of a di-substituted benzene. Any questions? All right, so let's go back to that topic I tried to jump ahead to, and that is, if we have a di-substituted benzene and we want to perform a third electrophilic aromatic substitution, where does the new group go? Okay, so let's look at the one I was drawing up previously, which we used as the example over here in our synthesis, para-nitrotoluene, we said that the methyl group is going to be an ortho director because the para position is blocked. The nitro group is going to be a meta director. So in the case where the directing effects of the two substituents reinforce each other, then we're in business because there's only one possible product that we can get. Okay, so the directing effects reinforce. We brominate in this particular case, and there's one product that we obtain. The bromine is going to be ortho to the methyl group and meta to the nitro group. Okay, but what happens if we have two groups where the directing effects do not reinforce each other? Okay, so here we've got para-chlorotoluene. The methyl group is going to direct ortho. Chlorine is an ortho-para director. It's a deactivator, but an ortho-para director. And so this chlorine is going to direct to this carbon. So we have opposing directing effects. Which group wins? The answer is the most activating group, or if they were both deactivators, the least deactivating group, meaning the group that's farthest up in position on the table, is the one that's going to control the reaction. So in this case, we have a weak activating group and a weak deactivating group. So the methyl group is going to control the reaction. If we're brominating, then we obtain this product as our major product. Questions? Okay. There's one more issue that we need to discuss in regards to di-substituted benzenes. And that is, if we have two substituents that are meta to each other, we cannot perform electrophilic aromatic substitution in between those two substituents. Okay? So let's look at meta-methyltoluene. Okay? This has another special common name, but we'll just call it meta-methyltoluene. Okay? If we're going to perform electrophilic aromatic substitution on this compound, we have a lot of choices. Right? This will be an ortho-para director. This methyl group is an ortho-para director. So we really only have one carbon where the substitution would not be favored. However, the carbon that's in between our two substituents is too hindered. It has a substituent on either side. Right? You can perform electrophilic aromatic substitution with one adjacent substituent. That would be an ortho situation, but not if you have two. So if we were going to chlorinate this compound, we could not chlorinate in between these two groups, and the other choices are equivalent to each other due to the symmetry in this molecule. So there's actually only one product that we would obtain. Okay? So no substitution occurs between substituents that are meta-substituted. Questions? Okay, so with all that information, then we should be able to plan syntheses of di-substituted benzenes, and we should also be able to predict the location of substitution if we're making a tri-substituted benzene. Now, let's talk about reactions that occur on substituents. Okay, so these reactions are not going to involve the pi electrons of the aromatic system of our benzene derivative. These are reactions that are going to transform one type of substituent into another. And these are going to be useful reactions because they will enable us to make substituents on benzene rings that we would not be able to install directly in a single reaction. Okay? So the first reaction we're going to talk about has its origins in the fact that a benzylic carbon-hydrogen bond is relatively weak. The bond dissociation energy for one of the benzylic carbon-hydrogen bonds in toluene is 85 kilocalories per mole. Okay? And that's weaker. Most of our carbon-hydrogen, sp3 carbon-hydrogen sigma bonds are in the 90s. Okay? So why is this one weaker than a typical carbon-hydrogen sigma bond? Think back to chapter 15 when we talked about bond dissociation energies. We talked about allylic carbon-hydrogen bonds. Trent?
Because if it's homolytically cleaved, then it will form a radical that can be resonance stabilized.
Okay, yeah. The product of the homolytic cleavage of that bond is going to be a resonance stabilized radical. We'll go ahead and draw that here. Okay. So this is the radical you would get if you abstracted one of those benzylic hydrogens. And in the same way we can delocalize charges into rings, we can also delocalize an unpaired electron into a benzene ring. Okay. And remember, spin density is the name of the term that we use for an unpaired electron. So what we're doing here is we're delocalizing the spin density. We're sharing the spin density across multiple carbons. Okay. So we're drawing the same sorts of resonance structures we've drawn earlier in the chapter. We're just using our half-headed arrows because we're moving an unpaired electron around the ring as opposed to moving a positive charge or a pair of electrons around the ring. Okay? All right, so what you see is that the benzylic radical is resonance stabilized. There's 4 carbons that share that spin density. Do we have a major contributor? And if so, which one? Is there something that one of these resonance structures has that the others don't? I would say so. Any differences? Okay, Brady? Yeah, this is the only aromatic resonance structure, so this will be a major contributor, and these will be minor contributors. But nonetheless, we have resonance stabilization with that spin density mostly on this carbon, but also delocalized onto these 3 carbons in the benzene ring. If you read the book on this topic, they drew another resonance structure where the pi electrons of the benzene ring were just shifted around. That's actually irrelevant in this case because that resonance structure does not delocalize the unpaired electron. Okay? So yes, it exists, but it's not relevant to our discussion of delocalization of the unpaired electron. So it's these 4 resonance structures that you would need to consider when you're thinking about delocalizing that spin density. So the ability to form a resonance stabilized benzylic radical allows us to perform a reaction called the benzylic bromination. Okay? And all you need is an alkyl group that has at least 1 benzylic hydrogen. And you can use the reaction conditions that we used for allylic halogenation. If you remember from chapter 15, the end of last semester, we learned about allylic halogenation, where we replaced an allylic hydrogen with a bromine. Now we're doing benzylic bromination. We're replacing a benzylic hydrogen with a bromine. Okay? So the mechanism is the same. So we're only going to look at it on the screen. We're not going to draw it on the board. Just remind us of what we learned in chapter 15. N-bromosuccinimide, or NBS, is going to generate a low concentration of bromine. And so that's why we're starting with bromine in this case. So we use heat, light, or peroxides to cleave that bond. This is our initiation step. And then once we have bromine radicals, we perform propagations, abstracting a benzylic hydrogen, That's the weakest carbon-hydrogen bond in this molecule because it generates the resonance stabilized radical. And that resonance stabilized radical will abstract a bromine atom from Br2, giving us the product, reforming the bromine atom. Don't worry about termination. That's going to happen, but that's going to be reversible because your heat or your light can just cleave that bromine-bromine bond again and allow us to keep going in the reaction. One difference between benzylic bromination and allylic bromination is that with allylic bromination, we needed to use N-bromosuccinimide. We had to have a low concentration of Br2. If we had a high concentration of Br2, then we would just brominate the double bond. We'd get a dibromide. Okay, we know that reaction's fast. We're not going to react Br2 directly with a benzene ring. That's not going to happen. And so that's not a problem with benzene. So with benzene, or alkyl benzenes, I should say, we are able to use either N-bromosuccinimide, or we can just use bromine Br2 in the presence of light or heat. And that will give us our benzylic brominated product. And then, of course, if we use bromine and a Lewis acid, iron tribromide, then we're going to get the electrophilic aromatic substitution. And I'll just write, I'm running out of room here, so I'll just write para-isomer. We would have two different products in that case, okay? So bromine with heat or light, or NBS, will give us our benzylic bromination. Bromine with a Lewis acid will give us the electrophilic aromatic substitution. So why would we want to attach a bromine to an allyl or a benzylic carbon? This sample problem sheds some light on that. If we want to make a compound with a double bond conjugated to our benzene, directly attached to our benzene ring, we do not have a one-step process of attaching an alkene. Right? We can attach a ketone, we can attach an alkyl group, but not an alkene to a benzene ring. So we need to be able to convert a substituent into a double bond. And we know that we can form alkenes from dehydrohalogenation reactions. We can take an alkyl halide and treat it with a strong base. So what we need to do is make an alkyl halide, and we do that by benzylic bromination, in this case of ethylbenzene, and then we use tert-butoxide to make the styrene. So that bromide here can then be transformed. You could also do SN2 reactions if you wanted. If you wanted a cyano group, or if you wanted to make an ether at that position, you'd have the ability to perform SN2 reactions in addition to the E2, okay? So benzylic bromination puts a functional group at the benzylic carbon that allows us to access other types of substituents. Any questions? All right, let's talk about oxidation and reduction reactions of substituted benzenes. And as we learned last semester, many oxidation and reduction reactions have complicated mechanisms. And the ones we're going to talk about in this chapter fit that pattern. So we're not going to go over the mechanisms of these reactions. We're just going to learn the reagents that are used and the types of products that are formed. Okay? So the first one we'll talk about is the oxidation of an alkyl benzene. To oxidize an alkyl benzene, we have to have at least one benzylic hydrogen. So I've drawn isopropyl benzene. We can oxidize that. Tert-butylbenzene, we could not oxidize. Okay, this will only work if we have one or more benzylic hydrogens. We use potassium permanganate. It's a strong oxidant. It can oxidize a variety of different types of compounds. When it reacts with an alkyl benzene, we generate a benzoic acid. Okay, this is benzoic acid itself. If we had other substituents, it would be a benzoic acid derivative. So again, we're not learning a mechanism for this. We're just learning that you have to have at least one benzylic hydrogen in order for this reaction to work. We cannot put a carboxylic acid group on a benzene ring by Friedel-Crafts type chemistry. And so this is a way that we can install a carboxylic acid group, put an alkyl group on, and then oxidize. Any questions? Okay, let's look at reductions now. We can reduce acylated benzenes or ketones. And there are two ways that we can do this reduction. One will use a zinc mercury amalgam with HCl. The other one will use hydrazine, which is like 2 units of ammonia stuck together, right? N2H4, in the presence of hydroxide, a strong base, okay? These reactions have names. You don't have to learn these names, but if names help you learn the reaction conditions, this is called the Clemmensen reduction, and this is called the Wolff-Kishner reduction. It's good to have two different ways to do this reaction, because if you had a more complicated starting material, more complicated benzene, you might have functional groups on that benzene that would react with your strong acid. And so then you wouldn't be able to do this reduction. But maybe they'd be compatible with a strong base. Conversely, if you had functional groups attached to your benzene that were reactive with a strong base, then you would want to use the other conditions. So that's why we have two reliable methods of performing this reduction, where we're completely removing our carbonyl group and we're ending up with a primary alkyl group attached to our benzene ring. So why is this useful? Let me grab the eraser here. It's useful because we have all sorts of problems when we try to attach a primary alkyl group to a benzene ring using Friedel-Crafts alkylation. So we take benzene, we react it with 1-chloropropane and aluminum trichloride. What product do we obtain? Anyone? Will we get propylbenzene? I'll give you a hint. We will not get propylbenzene. We will get isopropylbenzene because there will be a rearrangement. We went over the mechanism of that rearrangement. So we would not get propylbenzene. What do we do if we want propylbenzene? It's a two-step process. We're going to perform a Friedel-Crafts acylation. There's no rearrangement in a Friedel-Crafts acylation, but now we have a ketone that we don't want. In this case, we could use either of our reaction conditions. We're going to go ahead and use the Clemmensen reduction. Okay. Now we have our propylbenzene. So if we want to install a primary alkyl group that's longer than 2 carbons, we would have to do it with this two-step process, Friedel-Crafts acylation, followed by one of these 2 reductions. Okay? Ethyl we could install without reducing or without rearrangement. Methyl, of course, we could, but you can always just buy toluene anyway, so there's really no need. Okay, any questions about the Clemmensen or Wolff-Kishner reductions? All right, we'll go ahead and stop there. We have one more reduction of a different type to talk about on Monday, and then we'll talk a little bit about synthesis of complicated benzenes, and then we'll jump in to chapter 19.